Alright, so we're going to talk about solving trig equations. We solve trig equations, and what we want to do is we want to locate the solution on the unit circle. God bless you. And we want to give all possible solutions. So what this means is, okay, so here's our unit circle. Remember, x is cosine, y is sine. So I'm going to just throw a quick for instance. Let's say I have cosine of theta equals a half. Well, where does that happen? Wherever I have positive a half for x, that means that's part of my solution. So I have two solutions. I have pi over 3 and I have 5 pi over 3, but that's just one solution at pi over 3. When we're listing all possible solutions, remember, sine and cosine cycle in intervals of 2 pi. So that's what this is saying. I might say plus 2n pi, so if I say that, that's what I'm talking about, plus 2k pi. What that means is, let's look at our unit circle. Okay, here at this angle, at 60 degrees, cosine is a half. If I go plus 360 to that angle, cosine is still a half. If I go around one more time, another 360 degrees on top of that, cosine is still a half. So when we're listing all possible solutions, so remember my fake equation was cosine of theta equals 1/2. Well, theta is pi over 3, but in order to capture all those possible solutions, all the infinite solutions, I have to capture all possible rotations. So that's why we refer to it as plus 2n pi. And then remember, we also had another solution down here at 5 pi over 3. So we would also write theta equals 5 pi over 3 plus 2n pi. So when I'm listing all possible solutions, I'm listing both of these things because now I'm listing all the indefinite cycles when I start cycling around the unit circle, one time around this unit circle, another time around the unit circle, or another time around the unit circle. However, tangent cycles only in intervals of pi. So for tangent, we're going to write plus n pi or plus k pi. I don't care which one you use. If the instructions tell you to solve on the interval from 0, and here this should say, this is a typo here, this should say from 0 to 2 pi, not including 2 pi. This should be a parenthesis, so make sure you change that. From 0 to 2 pi, we would include between 0 and 2 pi, I can include 0 as a solution, but I cannot include 2 pi as a solution. So I have to make sure I'm reading the instructions just to see what they're specifying. Sometimes you might even see, oops, wrong thing. You might see something that looks like this as well. And what I'm going to do is I'm going to pull some homework problems into our notes today to make sure you understand some of these instructions. All right, so let's take a look at this first example. So here we have example 1. And we're going to solve. When we're solving, we have to list all possible solutions. Well, where is sine of theta equal to a half? So we're going to look at a unit circle, and we're going to determine where is y a half. And I know that the first solution is at pi over 6. My next solution happens at 5 pi over 6. This would be a solution set between 0 and 2 pi. But when I'm solving, if they didn't tell me to solve on an interval, I have to list all possible solutions. So remember, sine cycles at 2n pi. So I have to write plus 2n pi. So this represents all possible solutions. What I had in the beginning, just this, is just the solutions on an interval from 0 to 2 pi. But because it did not tell me to solve on an interval, I have to include all possible solutions. All right, let's make sure we understand it. Where's cosine of theta equal to negative root 3 over 2? So cosine, remember, is negative in quadrants 2. And in quadrant 2, we have negative root 3 over 2 at 5 pi over 6. And cosine is also negative in quadrant 3. And cosine is negative root 3 over 2 at 7 pi over 6. If I stop here, that would be solving on an interval from 0 to 2 pi. However, I'm not told to solve an interval, so I have to make sure I list all possible solutions. How do I make that happen? I just write plus 2n pi, and that would be our solutions. All right, here we have same concept. I want to know, where is tan of theta equal to -1? Well, tangent is negative in quadrant 2 and in quadrant 4. And in quadrant 2, tangent at 3 pi over 4, and in quadrant 4, 7 pi over 4. In order, remember, this is just on an interval from 0 to 2 pi right now. If I want to capture all possible solutions, for tangent, remember, it cycles in intervals of pi, so I would write plus n pi. All right, when we're solving, we want to isolate the trig function, and then we're going to carry out with the steps that we just talked about a moment ago. We're going to use the unit circle, and we're going to find where x is that value. However, our next slide says to verify that the given value is a solution. There was a typo on this slide, so what I'm going to do is I'm going to import something from your textbook, so that way we can answer that question. All right, here's something where we can actually work out. It says, verifying solutions in exercises 5 through 10, verify that x values are solutions of the equation. When you're verifying solutions, I want you to think back to what we did in sections 1 and 2. We just want to make sure that we are going to get the solution of, say, root 3 here. So let's start by substituting. And we're going to write tan at pi over 3 minus root 3 equals 0. We're going to add root 3 to both sides. And now we're going to determine, is this true? Well, what is tangent at pi over 3? Remember, we go to pi over 3. Good, it is root 3. So does root 3 equal root 3? Yeah, it does. Or I could write root 3 minus root 3. I could have left it just like this. It equals 0. So this solution works. This is a solution to it. I just verified it. So that's how you would do this type of problem in your book. Let's take a look at 4 pi over 3. Let's go ahead and substitute that. So let's do tan at 4 pi over 3 minus root 3. Tangent at 4 pi over 3 is also root 3. And I get 0 equals 0. So I just verified it. This one works as well. So that's how you do these type of problems. You're just substituting it and determining, does this solution work? If it does, then you verify it. If it doesn't, then either that one doesn't work out, or maybe we're doing something wrong. So go back and check your work, because typically these are going to work out. Now let's pretend this is from this slide, and I want to make sure, yes, there you go. All right, so I'm going to switch up these instructions. So now that I showed you something that is a proper verification, let's switch these instructions and say solve. Okay? So when we're solving, remember, we're solving on the interval. We're not solving on an interval. We're including all possible solutions. So I'm going to subtract 1, and I'm going to divide by 2, and I'm going to get cosine of x equals negative 1 over 2. Well, look at your unit circle and determine where is cosine negative 1 over 2. Remember, cosine is negative in quadrant 2. At 2 pi over 3, it's negative 1/2. And cosine is negative also in quadrant 3, and it's negative at 4 pi over 3. If I were solving on an interval from 0 to 2 pi, I would stop right here. But because we're talking about solving, we're including all possible solutions. So we're going to write plus 2n pi. And this means that if I kept going around 360 degrees from that angle, cosine will equal negative 1/2. So this is our solution for that one. All right, so here I want to do something similar. I'm going to subtract root 3, divide by 2. Sine is negative in quadrants 3 and 4. It's specifically negative root 3 over 2 at 4 pi over 3. And at 5 pi over 3. This would be a solution on the interval from 0 to 2 pi. However, I want all intervals, so plus 2n pi. All right, so let's solve this equation. When we're solving, we're going to do exactly what we were doing before. We're going to add 1. We're going to divide by 3. And I'm going to get this. But that's squared. I'm going to treat this, pretend this says x squared equals 1/3. What would you do? You would take the square root of both sides, right? So that's exactly what we want to do here. We're going to get tan of theta equals 1 over root 3. You must rationalize your denominator. And your solution looks like this. Tan of theta equals root 3 over 3. Now, where does tangent equal root 3 over 3? Alright, so our solution is pi over 6 and 7 pi over 6. But remember, tangent cycles in intervals of pi. So when we're including all possible solutions, we have to write plus n pi. Alright, so sometimes we might have to factor. Let's take a look at d. d is factorable. So here I can write 2 cosine x times cosine of x. And then in order to get this positive here, this has to be plus 1, and this has to be negative 1. Now that I have 2 binomials, I can set each binomial equal to 0. And then I can solve them independently. So here I get cosine x equals 1 over 2. And here I get cosine x equals negative 1. Well, where is cosine of x positive a half? Okay, so here are solutions. X equals pi over 3 and 5 pi over 3 for x, so cosine of x equal to a half. Cosine of x equals negative 1 at pi. Remember, in order to list all possible solutions, you have to write plus 2n pi. Alright, when it looks like this, what you want to do is, remember, when cosecant and cotangent are hanging out, if they're squared, then I can possibly use some Pythagorean identities. So that's my goal right now. I'm going to square both sides. So I'm going to introduce a squared component on both sides. When I do that, remember, we're foiling that binomial, we're squaring it. We're going to get cosecant squared x plus 2 cosecant x times cotangent plus cotangent squared x equals 1. Bring that 1 over, and now let's start substituting. Here we can substitute this term so that way I have multiple cotangents in there. Cosecant is equivalent to cotangent squared x plus 1. So that way I have consistent terms. So essentially that's what you want to do. You want to express everything on here in the same terms as possible, so that way maybe we can factor something out. Okay, so now let's start substituting. Here I get cotangent squared x plus 1 plus 2. Remember, I'm bringing over that 1 on the other side too. Minus 1 equals 0. So now I can combine like terms. I have like terms here, and I have like terms here. So when I combine them, I'm going to get 2 cotangent squared x plus 2 cosecant x times cotangent x equals 0. And now you can clearly see that I could factor out a 2 from both of these terms and a cotangent from both of these terms. So now finally that I have, and this says cotangent here, it looks like a plus sign. Now that I have the product of 2 terms, I could set them each equal to 0, and that's exactly what I want to do. So let's go ahead and do that. Here we get 2 cotangent x equals 0, and here I get cotangent x plus cosecant x equals 0. When I divide by 2, I still get cotangent x equals 0. Where is cotangent of x equal to 0? Okay, so here, divide by 2, you get cotangent x equals 0. Where does that happen at again? That's going to happen at pi over 2 and 3 pi over 2. But 3 pi over 2 is an extraneous solution. Remember, go back to that slide where I said typically tangent, cotangent, we look at those intervals from negative pi over 2 to pi over 2. Okay, when we look over here, Cotangent's equivalent to cosine over sine. Cosecant's equivalent to 1 over sine. So if I swing that one over to the opposite side, what statement of equality can I make from here? Are the denominators equal? Yeah. So what can I say about the numerators? They're equal too. Sorry, that was -1 because I had subtracted it from both sides. I apologize. And then yes, you get x equals pi. However, when we check it back into the given, this one is not going to work. Watch. Cosecant at pi is going to be, cosecant at pi plus cotangent at pi. Does that equal 1? Well, let's evaluate. When I plug it back into the given, cosecant plus cotangent, and I put pi, cosecant's undefined at pi, cotangent is also undefined at pi. An undefined plus an undefined is not going to equal 1, so that makes that an extraneous solution. So that one's not part of your solution set either. Okay, so that one's no. So technically, and the same thing's going to happen when you substitute 3 pi over 2. So here, your only solution that works it back in the given is pi over 2.